Okay, well, good late morning, good afternoon. Thanks for joining. My name is Felix Lalonde. I'll be your moderator for today. Thanks for attending what is part 2 of our combustion series. For those who missed it, part 1 was focused on the theory of combustion. So what is combustion, what's efficient combustion, and why we should measure combustion. Today's format's going to be a little bit different. We envision a panel discussion, which means we need lots of input from you guys. Our two panelists for today are going to be Stuart Simmons and JC Arens in front of you. Before we get started on the whole discussion, however, both Stuart and JC are going to do a short presentation. Stuart is going to focus on what we'll call conventional combustion methods, and JC is going to talk to us about tunable diode laser analyzers, or TDL for short. So again, we'll need lots of input, so feel free to ask questions. I'm going to go over 3 rules really shortly. The first one being during the first phase, during the presentation phase, all microphones are going to be muted. If you have questions, please feel free to write them in the Q&A section. So Q&A up top next to chat and polls. Afterwards, once the presentations are done, Gada is going to have a really short poll for you guys to answer. She's also going to unmute all microphones. And from that point on, please be mindful of your microphone status. If you've got a question, please use the raise hand function. Either myself or Gada, we're going to point you out and let you speak, interact with our panelists. And yeah, lastly, this webinar is recorded, so please be aware of that. You'll all get a copy, but just in case you're not comfortable. And that's about it. So yeah, Stuart, JC, I'll let you guys introduce yourselves and get started. Thanks.
Thank you, Felix. Thanks, Gada. Thanks, everyone, for joining. Yeah, good morning, good afternoon, good evening, wherever you end up being. Very happy to have you back. Hopefully no technical issues this time for anyone who was there the first one. Hopefully we've ironed all that out. But for those that haven't met me, my name is Stuart Simmons. I've worked in analyzers my entire career, having started out as an analytical chemist, but I've worked in the process industry for a long time now. And I've notably done it on a number of sides of the fence, either with major manufacturers or distribution companies such as Novatech, and in a number of places around the world. And as such, I've spent a great deal of my career working in and around combustion control, as we'll talk about today. JC, you want to introduce yourself?
Yeah, thanks, Stuart. My name is JC Arens. I look after sales and service for Novatech. I too have been working in and around the world of analyzers my entire career, having gone through all the stages from inside sales to outside to some BD and now more on the management side of things, but always with a keen eye towards being an analyzer specialist and supporting our salespeople with these more advanced discussions.
JC, what I'd like to do now is give you a very brief recap, and I'll give you an order of the day just to follow in with what Felix said. We won't go back over Novatech. I think for most people on the line, you know who we are, but we're a distribution company that offers services in the analytical industry, process analytical industry, coast to coast. And we do sell, of course, a conventional combustion analyzer and a tunable laser diode analyzer. So we have that experience within our arsenal. We won't be talking directly about the products we sell today, but it does give us that experience on knowing which ones go where and where we put them. And as we mentioned earlier, we spend a great deal of our time doing combustion control because it's such a big portion of the process analyzer business. We'd like to spend about the first, let's call it 20 minutes here, just recapping the last webinar for those that weren't there, looking a little bit at the technology. The one thing we didn't do in the previous webinar, it was all theoretically based, is talk about the technology itself. And we thought we'd spend just a handful of slides on both techs today, just so we're familiar with it. It was one of the questions that was raised immediately after the last webinar about, okay, what does the technology look like? So we'll answer that question today as quickly as we can. And then we will, as Felix described, stop and invite all the questions. There's always lots of stuff to talk about with combustion control. So we'd like to then spend the majority of our time here talking about that. Okay, let me jump in. What is combustion control? I have 3 slides to recap the previous presentation. Well, combustion control is effectively everything we do all the time for all of us, whether we realize it or not. But we are all little combustion furnaces operating on a continual basis. And we can extend that logic, the very same logic, into our process world. We take in food, we breathe in air, by respiratory work inside of our cells, we generate energy and carbon dioxide and water. That is the exact same process that takes place in all industrial areas. And we've known it for a very, very long time. If you end up spending any time within that world, then you know that you will spend some time doing combustion control. The question in hand is, how do you make it efficient? And what does that mean to be efficient? And how do I maximize the ability of what we do? Sadly, for us humans, we all know some of us are better at being combustion control experts than others. And there is an ability to enhance and nurture and make better all of those things. The same logic applies in the process world. Where it ends up, I like to distill it down into relatively simple terms. And effectively, in the process world, it will fall into one of these three camps where you will see combustion control analyzers. Process heaters are effectively just as the word describes, we're just heating something up. So much of the world does better. We can operate reactions and events that take place in the process world at heat, and we need heat. So we just generate heat to warm things up, to make a reaction move, to keep something warm, do a number of events. They are nothing more than they describe. They just warm things up. And there are lots and lots and lots of them out there. The second version of it is a steam boiler. We use a huge amount of steam in industrial process because it is one of the better ways to maintain heat and to heat things up and to move heat around from one place to another. We can generate much higher temperatures and hold that temperature in. There is whole another world of discussion for webinars about quality of steam and looking after steam. It's a headache for many people that work in plants, but we have to generate a lot of heat to make the steam in the first place. So that's a big portion of what we do. And finally, the last one is thermal oxidation, incineration by any other word. And depending on where you are, it's a much more diverse industry. It can be anything from a clinical waste incinerator in a hospital to a crematoria to the back end of a sulfur recovery plant where we're finally ridding ourselves of the sample. Generally speaking, we like to, although it's somewhat counterintuitive to some people, we like to burn things at the last minute because the burnt version of them is better than emitting the original version of them. H2S being a classic example. We don't like SO2 going up into the atmosphere, but it's better than the H2S going up. So at the very last minute, we oxidize it. So those are the three main areas you're going to find it. And within that, all the devil lies in the detail in there. It becomes a very complicated world for our combustion engineers to maintain and look after and optimize any one of those three processes. The business of process analyzers, if we take another step back, and I'd mentioned this previously, there are three major reasons, I like the word three, major reasons why you might buy a process analyzer. And generally speaking, it has evolved through the efficiency, the history of the industry itself. Efficiency is the first reason, making sure you get the job done and maximizing your profits. Safety, which has grown over time and thankfully is much more prevalent these days than it was, say, 30, 40 years ago. And then lastly, emissions, that we now do have a very tight control on what things go out into the atmosphere and how we monitor that and look after it and reduce it over time. The great thing about combustion control is like a 3-for-1 here. If we do our combustion efficiency control measurements properly, then we tick the efficiency, we tick the safety, and we tick the emissions all at once. My little graph here is showing you roughly how that works, and we talked about it before. As long as you've got some amount of excess oxygen at the back end of your process, then you can be relatively confident that you burnt all your fuel. But that doesn't give you efficiency, it just says I burnt all my fuel. If you want to start to be efficient at the same time, then you need to think about the incomplete version of combustion. And thankfully, in the world of hydrocarbons, we have an interim stage of incomplete combustion. And we call it combustibles or CO. JC will talk about it directly as CO. In my side of the fence, we're going to talk about it loosely as combustibles. But what it means is, in my reaction of burning a hydrocarbon to carbon dioxide, water, and heat, if I don't quite do it properly, instead of making carbon dioxide, I can start to make carbon monoxide. Instead of making all of that water, I can leave behind some hydrogen. And those incomplete versions, partially complete versions, are an idea of efficiency, and I can monitor for those. So most large process analyzers now monitor for the combustibles rise. And in my picture here, that's that very, very steep red that you see on the left-hand side. If I add into my analyzer an oxygen measurement for excess oxygen, and then a combustibles measurement, which in theory should be almost zero or close to zero, and watch for it to occur, then I can start to understand the efficiency of what I do. My third little tick point here is, if I am perfectly efficient, I am also reducing the chance of emissions. So I can tick my efficiency, my safety, and then my emissions by looking at combustion control. And really, that's the primary basis behind all the analyzers that we do. How do you get to combustion control efficiency beyond the analyzer? Well, that's when we talk to combustion engineers, and you realize that it's a very, very tricky process. It depends on what you're burning. It depends on the turnover, the speed, the efficiency of control within the plant, the age of the plant, whether there are leaks and holes, whether my burner tips are in good shape. There's a million reasons why it gets very complicated quite quickly. But don't despair. There are a number of known things that we can work with. And I left this graph up here because it does that for you. It tells you a couple of things. You never want to not burn enough. That is not only incredibly inefficient, but it's also very dangerous. Safety runs out of the window and it coats the whole plant up, and you have all sorts of problems. So excess oxygen is great. But as you see in my chart, the little pink line going down the middle, wonderfully for us, the most perfect efficient point still has excess oxygen. So that's a fantastic point to start. My oxygen reading should never be zero. And that's a wonderful thing in process analyzers, because you have a dynamic line to start with. What we do know in addition to that is, if I add in lots of air, lots of oxygen, then I give up some efficiency. And if you run the numbers on a big plant, that can be millions of dollars for sure. But you give rise to this potential for huge amounts of emissions to rise. So what we do know is oxygen only is not enough. You do need to know the amount of combustibles that you could effectively get in order to know where your efficiency line is. It's dynamic. My little graph there showing you whether you burn coal or oil or gas shows you that the perfect excess oxygen number is very dynamic depending on what you do. And then you throw in the plant design and all those other things, and dynamism becomes larger and larger and larger. So it's not an exact science. There is no what is the right number. It depends on plant and a number of other factors. But with the right measurements, you can actually get to the point where you're pretty sure you're as efficient as you can possibly be. All right, that's the previous webinar. We do have it available for people should they didn't have it last time, and we can certainly send that out again. So don't hesitate to ask us if you want it. The world of process analyzers has changed over time, of course. It's dynamic and it's evolved. Since about the 70s, zirconia dioxide has taken over the world of combustion control. Prior to that, it was paramagnetic analyzers and extractive versions. But let's say the last 50 years, almost everybody has used some version of zirconia dioxide to make their combustion control measurements. In about the last 20 of those 50 years, we started to see the rise of tunable laser diode technologies and where they fit into the industry. JC's going to speak to those, and then hopefully in the panel discussion afterwards, we can talk about how the two knit together in terms of your solutions for combustion control. But let me tell you quickly about the conventional version. In the 70s, some clever person came up with the idea of zirconia dioxide as a methodology for measuring oxygen. How and why? Well, zirconia dioxide is effectively a ceramic. By any other means, it looks like a ceramic when you look at it. If you have a chance to ever look at one, there are tube versions, there are disc versions, but you can see them and you will see very much that it looks like a ceramic. Within the design of that ceramic, which is effectively a lattice of structure, there are holes, chemical holes. And in our case here, particularly in zirconia dioxide, there are oxygen ionic holes. It turns out that when we heat that ceramic up to a temperature, and in the case of zirconia dioxide above 600, those holes become the perfect site to migrate oxygen ions. So we can make a movement of ionic oxygen from one side of the ceramic to another at a given temperature, as long as it's above around 600 C. It's very important to fix that temperature, and I'll talk to you about that in a minute. But above that temperature, we can ionically move oxygen across the surface of a lattice structure. How do we do that then in practical terms? Well, what we do is best to look at it on the picture on the right-hand side. If on one side of my ceramic structure, I have a reference gas, and in this case, air, so I just pass air on one side, and then on the other side, I have a sample gas. If that sample gas is also air, then I have a balance of ionic exchange from the reference to the sample side. And what I get is zero migration of ionic change, and I get 0 millivolts generated across the two. If I were to change my sample to something less than 21% oxygen, so in the case of combustion control, I bring this all the way down to 2, 3, 4, 5%, then I have a differential between the reference side and the sample side, and now I can start to migrate oxygen ionic exchange across the surface. That migration is a millivolt signal to me, and I can use that millivolt signal in this thing called the Nernst equation to understand how much oxygen I have. There's a couple of practical implications to understanding that. One of them is it's logarithmic and inversed. So all that means in real terms is the bigger the differential, the more millivolts I generate. So the really nice thing about zirconia dioxide technology is actually the further you come away from 21%, the more millivolts I'm generating, the more accurate I'm actually getting. So that's why we love analyzers to be calibrated at a very, very low oxygen concentration, because actually I'm generating a massive amount of millivolts. The other thing to note in here, practically, is temperature is in the equation. So temperature stability is very, very important. That speaks to a couple of things. If you do in situ oxygen, with oxygen-only sensors on small package boilers, which are still quite common to this day, then temp control becomes quite important because the sensor is on the inside. And I have a picture I'll show you in a minute. But understanding that temp control is quite important. If you do the more industrial versions of the analyzers and have the box on the outside and aspirate the sample out, again, I'll show you a picture in a minute. Now we are back in control of this temperature. We can heavily fix and control the temperature around the zirconia dioxide, and that makes even more stability within the reading. So nominally, most people fix it around 700 degrees C is the most common place to be, but stability and temperature control around that sensor becomes very important. Once you do that, then it's a very, very simple equation between the reference and the sample and this exchange of millivolt signals. That's the oxygen side of the business. On the combustible side, from a conventional point of view, we use a relatively simple combustion technique, catalytic combustion of some form. And all we're trying to do here is to complete a reaction that didn't completely take place in the first place. If you burn methane completely, you take CH4 with oxygen or air, let's just call it oxygen for now, and I create carbon dioxide, water, and energy, just as I do when I breathe in and breathe out and have my breakfast. If I don't do it efficiently, unlike my body, which doesn't do this, if I don't do it efficiently in the process world, instead of making carbon dioxide, I can make carbon monoxide. I didn't have enough oxygen. I didn't mix it properly. I didn't give it enough residency time. My burner tips weren't working very well. Whatever that is, then I start to make incomplete combustion. And as it turns out for us, it's an extremely handy interstitial step in the world of process, because now I can start to evaluate when it's not right, wrong. I think I'm going wrong. I haven't completely gone wrong yet. I'm just starting to see something that's not working effectively for me, and how do I deal with that? So we use these catalytic detectors to effectively complete the combustion cycle. I take that CO, I apply a little bit more oxygen, and I make carbon dioxide. Or I take that little bit of hydrogen, I apply a bit more oxygen, and I make water. And I do that on a bead, and I reference it. There are effectively two types over the history of the industry. Some people have moved on from hot wire. Some people continue to keep a hot wire version as well as the more modern one I'll show you in a minute. Hot wire is effectively just as it sounds, and we're somewhat familiar with them in other technologies like gas chromatography, those sort of things. But effectively, I have two beads. One of those beads is coated with an active catalyst of sorts, usually some sort of platinum coating. And that's where I want my reaction to take place. My CO plus a half oxygen to CO2, that's where I want it to take place. The other bead is uncoated and the reaction will not take place there. If I stabilize the temperature of the two and call that 0, then when the reaction takes place on the bead that is happening, because the CO does exist, then I get a temperature differential between the two. I can understand that as a volt signal, and I can relate that to concentration of CO. It's a relatively primitive version of the analyzer, but it's also a little tougher. It has a bit more muscle behind it and can stand up to dirtier samples a little bit better than others, but it isn't quite as sensitive. The follow-on version, which has been around some time now, in the last 20 odd years or so, is a version of a thin wire RTD type detector, which does a couple of things. It's more like a Wheatstone bridge. It works in exactly the same way. We catalyze 2 quadrants of it, and we ask those to do the reaction, which then imbalances the bridge, but we're picking this up in ohms, so it's much, much more sensitive, and therefore we can get to lower readings. As the industry has wanted to get itself to more and more tighter control, then the RTD detectors become a much better option for a lot of people. Certainly if you think around Alberta, where I happen to reside, where we burn a lot of natural gas, then we can consider readings of very, very low excess oxygen and very, very low CO readings. So the RTD then lends itself if we're trying to look at less than 50 ppms and control between 50 and 100. If you were adding some plant gas that's got some sulfurs in it, then you might want to go back to hot wire because it'll just stand up to the job a little bit better. So we keep 2 of those technologies around, but that's how they work. They work in tangent with the oxygen to understand what's going on. One final note before I hand over here, can it measure methane? Can it measure uncombusted hydrocarbon? And the answer is no, strictly for the reason that it's not hot enough. So my combustible sensor doesn't have enough activation energy to burn methane. But there are sensors that can be converted to do the job. And we are starting to see this rise, and it's a lovely lead-in for JC to discuss it. But we're starting to see the rise of a safety measurement that says, what happens if I just didn't burn any stuff at all? What happens if half of my burner tips weren't working and I got a pocket of gas come around the combustion zone? Well, you can put in these kind of sensors that are activated at that higher temperature to say, oh, I see hydrocarbon, you've got a problem, you need to shut down safely. So there are versions of that, it's worth noting, and we are starting to see more and more folks be interested in that version of it. My final slide before I hand over is just one on design control. The top picture is in situ oxygen only. The sensor is inside the process. It's measuring hot and wet inside. It's a relatively simple device, but it's very good for low package boilers. The critical point here is the sensor has temp control. It's my Nernst equation, and it's quite important. So I can't be in a zone that's too hot and will mess with the control of my sensor temperature. If you want to get to the more industrial version, then you flip to one of the 2 below that. And there are sort of 2 flavors on the market. One is a low flow, small volume, pass it through very small sensors version, which is the one in the middle. And the one at the bottom has effectively 2 loops. One is like a fast loop in the bottom, which means it can drag a much bigger sample and be a bit more aggressive. And then it has a secondary loop above it to make the measurements itself and pass it back. But these are what we would call close couple extractive, ex situ. So there are a number of versions on the market, but critically, we keep the sample hot and wet. We don't mess with it too much, and we can deliver a reading as quickly as we possibly can, because in combustion control, of course, that's critical. All right, I'm going to hand over to JC. So that's the very basics of the technology from the conventional combustion side. I'll hand over to JC, and he can show you the TDL new version of technology. JC.
Yeah, thanks, Stuart. Let's just jump right into the first slide because I think it tells the story we want to see here. Next slide, please. There we go. So TDL, by any other name, really is simply an absorption technology. It's optical absorption spectroscopy. If you're familiar with how non-dispersive infrared or even UV analyzers operate, TDL analyzers are no different. So the equation that we deal with instead of the Nernst equation is based on the Beer-Lambert law, The things that are important here, and we will come back to this, are the last two components. So we have absorbance being a function of an absorption coefficient that's specific to the molecule that we're trying to measure at any given time. But then the other two, the path length and the concentration, play into it as well. And that makes perfect sense. So for a fixed path length, the only thing that will change absorption is changing the concentration. But for a situation where the path length potentially is a factor, and it can be, and we'll talk about that in a few minutes, we have to be able to control that to ensure that we don't get variability in absorption based on both concentration and the path length. Next slide, please.
Coming.
There we go. Thank you. So what is the difference between a laser and a traditional non-dispersive infrared analyzer? I like to think of it as a much smarter lamp with a dumb detector versus a traditional analyzer being a dumb lamp with a smart detector. So let me explain. In a traditional infrared gas analyzer, we have some form of infrared energy, a lamp, we'll call it, that is emitting energy across a region of the infrared spectrum. And then we use techniques such as either optical absorption filters, or perhaps a detector that's tuned to a specific wavelength, or gas filters of some kind using the gas itself as a filter medium. But all of that is done to ensure that we look only at the wavelengths or the region of the spectrum that interests us currently. TDLs do it the other way around. So with a tunable diode laser, we have the ability to control the wavelength at which our energy is emitted. And that's the clever bit about TDL. And we can control it incredibly well. If you see the little image to the left, some of the stats that are there, the width of the laser is only 0.0001 nanometers. I'm struggling to read it with my glasses on here. So it's tiny. It's absolutely tiny. And we have the ability to control that wavelength of emission across a region. Now, it's not a big region. It's a very finely tunable wavelength, but still, we're looking at a region potentially 0.2 to 0.3 nanometers wide. What does that mean for us? It means that we can pick an individual absorption line. These are known as peak fine structure for the molecule of interest. In the case of combustion, the traditional ones, obviously oxygen, carbon monoxide, methane, potentially hydrogen even, and scan over that peak. We can look to the left of it, to the right of it, right on the center of it, and we get a tremendous amount of data and effectively can map out the shape of that peak over a small region. So it's a very, very powerful technique that way. Next slide, please. So what do they look like? Thinking back to what I said earlier about the Beer-Lambert law and why it's important to understand the L component of our equation, or the length, the distance. TDL has been adapted as a technique first and foremost as an in situ technology, and that's what we care about for combustion applications. Something that's mounted directly to the process. We don't have to deal with some kind of extraction system, no sample conditioning system. TDL technology has evolved over time, and there are analyzers today that are designed with an extractive form factor. So it's not exclusive to the in situ format, but for the purposes of combustion control, this in situ format makes a lot of sense. However, keep in mind that what we're dealing with is an absorption technology. I have to have a lamp, and I have to have a detector, and I have to have a region in which that energy interacts with the gas that I'm trying to measure. So the way these are traditionally set up is a transmitter on one side of the process and a receiver on the opposite side of the process. And those have to be aligned with one another. So each instrument requires two nozzles typically. The other thing to keep in mind is that that laser can only be tuned across a small region of the infrared spectrum. Typically, we can only measure one gas per laser. It's just a happy coincidence that CO and methane, or carbon monoxide and methane, happen to absorb in regions that are similar, and we can use a single laser to measure those two components. So in the case of a traditional combustion analysis where we would want to do all three of those components, oxygen, carbon monoxide, and methane, we can do it with just two analyzers or a single analyzer that combines two laser modules into it. But again, always with that form factor in mind of transmitter on one side, receiver or reflector on the opposite side. We can't get away from that. So it sounds like a great technology. It sounds fantastic. But as with all technologies, there are challenges. And in the world of spectroscopy, there are things that impact our ability to do the measurement, which we may not have control over. Things that are happening in the background, be it pressure, temperature, the presence of other molecules that we didn't anticipate, those can all have an impact on our ability to do the measurement. Nonlinear baselines, the distance that I'm trying to do the measurement on. Think back again to our Beer-Lambert law, distance has an impact on the absorption. If I'm trying to do a measurement across an ethylene cracking furnace that's 30 meters wide, then there will be a tremendous amount of absorption that takes place between my laser source and my detector, and I need energy to get to the other side. I measure absorption changes. I need to be able to see some of the energy make it to the other side. If there's too much interference or absorption taking place between my source and my detector, I can't do the measurement anymore. So these are challenges that have to be thought of. Conversely, the opposite is true as well. If I'm trying to do a very low concentration measurement, my CO, for example, in parts per million, and I have a very small diameter process where my transmitter and my receiver are close together, I may not have enough space between the two of them to have sufficient absorption take place to get a reading. So TDL is one of those technologies, because of its nature, because of the fact that it's mounted in situ, that has to be thought of from the complete application perspective. It's not a question of whether or not we can measure these molecules. The question is, can we measure these molecules on your specific process? That has to be the way we approach all of these applications. Next slide, please. So the challenges have been met. A lot of the companies today are very advanced. This industry, as Stuart pointed out, is relatively new in the world of process analytics. It really kind of took off in the 90s. And I would say the adoption of the technology for combustion control is really something that is from the 2000 onward. So it's young compared to other techniques such as zirconium dioxide. But what's changed tremendously is not the physics of the technology, it's what we can do in terms of mathematical manipulation of the signals. The processing power of the analyzers can do incredible things that we couldn't even think about in the past. Situations where maybe the baseline is not flat, or there's no way to do a normal fit to that baseline. In the past would have meant that that application was not possible. Today, with advanced mathematics and multivariate analysis that's built into the software from these manufacturers, we can deal with that oftentimes. Next, please. It's the same thing with the dynamic range, that ability, that signal to noise ratio that we're able to obtain nowadays with the instruments means that even with only 0.05% of the signal making it across from one side to the other, I can still do a measurement. And that's incredible. That means that we can now do distances that were unheard of in the past. 30 meters, yep, I'll do that, no problem. So there's really tremendous gains that have been found in the last few years based on what we can do in terms of cleaning up the signal and the mathematics that can be applied to it after the fact as well to clean up that signal. Next, please. And then finally, the interferences. We talked about the fact that carbon monoxide and methane can be measured with a single instrument, but that's a big but. If I have a situation where one of those two components, and typically it will be the methane, has a tremendously high concentration relative to the carbon monoxide, will it completely mask my signal for the carbon monoxide? And that can happen in the real world in the types of applications we're measuring. The newer software is able to work that out. And that little example that we see in the lower graph, a process with 21% methane and increasing levels of carbon monoxide, and we're able to track it linearly, despite the fact that we had that huge interference from the methane adjacent to the carbon monoxide peak. Next, please. So talking about this technology, we now think about it from a practical consideration. It is an optical technique, and it's not going to work if my optics can't transmit the light or receive the light on the other side due to some kind of fouling on the windows or obscuration. So there are things to think about in terms of purging. We use purging for two reasons primarily. One is to ensure that the process does not make its way onto our windows and foul them. So that's super important. It means that our system will work trouble-free for extended periods of time. But the second aspect is back to our Beer-Lambert law, and that is that L factor, or the distance that we traverse. Looking at the lower image, we can see a chimney or a stack that's relatively small in diameter, and nozzles with isolation valves on it that are filled with potentially the process gas of a greater distance overall than my entire process. So if you sum up the distance that the laser has to travel through those two flanges on either side, it's greater than the distance it travels in the process itself. So if there's variability in the composition of the gas within the nozzles, if I have process gas going in there and creating eddies or currents, or maybe there's stagnant pockets of gas that are not reflective of what's happening in the process itself, it's going to falsify my reading. And so the best approach there is to ensure that those nozzles don't play a part in our analysis. We purge the nozzle. We remove the component of interest from the nozzle. Classic example is if we're trying to measure oxygen, we purge the nozzle with nitrogen. That way the nozzle no longer plays a part. It's no longer part of the optical path length that I'm measuring, and the optical path length that I'm measuring is limited to the size of the stack itself, or we can use insertion tubes to control it even more finely. And you can see an image of the insertion tubes top right in your image there. Next slide, please. So in order to do that well, or to do it correctly, we also always provide an accessory panel with any of these installations. And the idea here is to provide control for the user to properly do the purging, but also to allow the capability of sending a gas up to the instrument in order to validate its performance. In the case of the analyzers that are mounted on the stack that do an ex situ measurement, we can control what is being measured within that instrument. We can effectively block off the process and flood that instrument with a gas of interest and do a measurement and validate that its performance is correct. When an instrument is mounted directly on the process, we can't do that. I can't just shut off the process and fill your stack with a validation gas. It's just not possible. So we do that externally within a defined path length that sits within the laser's path, a little cell, and that can be done on demand, it can be done manually, it can be done remotely, but we can fill that cell whenever we wish with a gas of interest and look for that step change in concentration that occurs when we introduce more of the gas that we're trying to measure. I think that's it for my section.
Yeah, thank you.
Thank you.
Thanks, guys. That was great. So great that we got no questions. So I think we'll go straight into the poll. I'm going to invite anyone to answer the poll, but afterwards think of questions, maybe just to get the ball rolling. It can be any question. And yeah, JC and Stuart are going to be happy to answer those.
Absolutely.
If you get a little nauseated by the windows moving as soon as someone speaks, you can actually go in more, which is the 3 dots, and then change layout to tiled. That should fix everything. So the poll has been posted in the polls tab.
It's good. There's a good mix. It's a good mix, and interesting. There's a number of people that have both, which is fascinating.
Absolutely.
It seems that one technology meets up with another one, a conventional one that's been there a long time is added into with the TDL technology, that one wonders if that one is going to take over from the other. And effectively, historically, that's exactly what zirconia did to paramagnetism in the 70s. It just literally came in, was a smarter idea, ticked a number of boxes that the conventional one couldn't do, the paramags couldn't do, and took over. So today you'd be hard pressed to find anywhere in the world that's doing extractive oxygen measurements on combustion control. But in the case of lasers, I think, as we've watched it unfold in the last 20 years, it seems to me that there are practical considerations for why you either want one or the other or both. And I think in some of the large industrial processes now, it seems logical that the journey is towards needing some conventional combustion in the lower regions in a number of spots, and then having some laser diode technology above it to make sure that you're covering off on and not missing anything. And that seems to be a fairly common approach to it. There are some applications, of course, like ethylene crackers, for example, that are very large and very, very hot, that have gone almost exclusively to things like lasers. And then there are some applications where inside is an awful lot of tubing runs where we're warming stuff up, where practically you can't shine a light across that thing. It's impossible. That will always remain as a conventional probe in, being in situ into the process. So it seems logical that looking at our poll, we would end up with that answer. So some with this, but some with others, and with the combined. I think that's probably the future of the industry. JC?
Yeah, I think
Stuart,
that makes perfect sense.
or JC,
Yeah.
before you guys get going, I'll just remind anyone and everyone that microphones have been unmuted, so you'll have to manually mute yourselves from now on. Carry on.
Yeah, I agree with you completely. It's when the lasers were introduced, there was a bit of a feeling, I think, from the industry, well, that's it, this is going to take over, and not just for combustion applications, for other technologies potentially, that this was going to replace. And as with everything, there's a little bit of that, and then the reality sinks in and people realize, oh, no, this is where this is very good for. This isn't necessarily a replacement for that. And I think we've settled into where it makes sense in terms of from a measurement perspective, from a practical perspective. There are different challenges with each technology in terms of how you operate it and how you maintain it. So there's always kind of that balance between the two. Sometimes one makes more sense than another. Sometimes both make a lot of sense.
Great. So let me maybe ask Stuart about the difference in oxygen readings between, let's say, zirconia and TDL, what that means for the industry.
Yeah, it's an interesting one, and it's one that comes up every now and again. And the question is, effectively in reverse, do you burn oxygen on your combustible sensor? And the answer, of course, is yes. If you imagine my system, as you bring it into a conventional analyzer, you have to measure the combustibles reading first and then the oxygen, because the combustible sensor, depending on how much of that reaction is taking place, requires some oxygen to take place. So it takes a little bit of the excess, a half oxygen plus the CO reading gets me to CO2, and I burn a little oxygen. And effectively, that's what they would call residual oxygen. By the time I look at it at my zirconia sensor, I am minus the bit that required all the combustion control. For a laser, of course, it won't work that way. It's an optical measurement. You will measure the oxygen as it's seen in the process. There is some argument that those two are greatly different. In practical reasons, I think that nowadays you tend not to see such large runaways of high CO. There's a lot more safety involved. There's a question here about SIL, which we'll bring up in a second here, which relates to that conversation, which is we don't let our plants run away anymore. We don't see huge excursions of CO. And because you don't see huge excursions of CO, you don't tend to burn a lot more oxygen to get the measurement done. So the difference between true oxygen and residual oxygen can be very, very minimal. And if you are, depending on which manufacturer you are, you'll make an argument in either direction. I think practically, I'd probably say that there are other factors that you would worry about more, whether you've lost a little bit of oxygen in the reading. But If it comes up at a trivia quiz at any one of your plants, is there a difference between the two? Absolutely. Your CO combustible sensor will burn a little bit of oxygen to get the job done. Let's jump into this
Great.
question I see in the chat about that,
Yes.
because that does relate to. So the question is about whether there are any analyzers that are SIL rated. And the answer is yes. There are, both on the laser side and in the conventional combustion side now, SIL rated analyzers. It's sort of been driven, by a North American thing largely, and it relates to the reliability of analyzers. As an aside, quickly, almost no process analyzers are in control. We are usually fact gatherers for a plant to tell them whether they do or don't like what's going on in their plant, but they're in control. There are very few examples of an analyzer directly controlling any portion of the process. Combustion control is that rare exception, and a version of it in tail gas analyzers is another exception. But occasionally, should the analyzer be believed enough, it can do two functions. It can operate a trim valve to look after the amount of air coming into the process to optimize combustion control, and it can also be part of a boiler management safety integrated shutdown system should they not like the readings and feel that the plant is now losing control and is potentially heading towards an extremely dangerous situation. So yes, both technologies are now found their way towards doing that, and they normally do it in terms of reliability. So they build enough data into themselves from a diagnostic routine, upkeep, uptime, preventative maintenance methodology to say, you can rely on me. I have accredited myself to SIL 2, and I've proven that through the data and been given that option. And you can get it both in TDL and in conventional combustion analyzers these days. JC, anything to add there?
Yeah, absolutely right. And I think even through third-party accreditation as well, there are agencies that will actually review that reliability data and put their stamp of approval on it to state, yes, this is a SIL 2 rated instrument.
Okay. Maybe one for JC. It's kind of going to involve both, but can you speak to us a little bit on the differences between both technologies and both approaches regarding CapEx versus maybe OpEx, operations versus purchase cost?
Yeah, and that's a great question. It speaks a little bit back to what we talked about earlier in terms of the overall picture when we're looking at the installation and potentially the long-term operating costs. There's no doubt that from a CapEx perspective, TDL probably will be more expensive. The instrument costs aren't that significantly different compared to the ex situ or the close coupled extractive. It's more the fact that it's going to require a second nozzle if we're going with a cross stack, if I want to call it that, technology, and potentially a second set of nozzles, depending on which instrument we're looking at. If we want to go for the full oxygen, carbon monoxide, and methane, for example, that would require two instruments, which means two sets or two pairs of nozzles. If those nozzles aren't there already, that's a factor for sure of consideration for customers, that they may have to wait until there's a shutdown potentially to install those nozzles on their process. From an OpEx perspective, I would say that really the main thing is the purge gas. The technology itself does not require periodic calibration. It can be validated as needed, either on stack or even off stack if you really wish to check it. And more often than not, that's more of a customer driven requirement. They may have procedures to say, we need to validate this monthly or something of that nature. But really the only consumable then becomes the purge gas. And that's not insignificant. There's a cost associated with instrument air. There's a cost associated with nitrogen. So with that gas flowing on a continuous basis for these analyzers, that is certainly something to be considered. Stu, do you want to talk about the same on the conventional side?
Yeah, the only caveat I would add in, because it absolutely 100% correct, JC, is that potentially, depending on the design of the plant, you could see yourself having a smaller number of analyzers in total. So if you're a large plant, you might have, say, 10 conventional analyzers in place you might be able to see a version of your future where you only need 3 or 4 laser pairs to deal with the same job because you're covering a much larger area. And that is the inclination of the industry, I think, is to see it in that term. Can I rid myself of all of these analyzers and just put 1 or 2 in here? And the initial answer is often yes. Why not? You put it right at the top across the economizer or across the above the convection zone, and you shoot across and you see everything down below. There might be 10 burners down below, and you see all of it coming up past that laser. The problem becomes a practical one, which is, well, what happens when something isn't right and you don't like the look of the number? How do you identify the source of the problem down below if you haven't done it? If you've tried to sort of do a one-size-fits-all coverage above it. And that you realize in the end that now diagnosing a problem below becomes a bit of a challenge, whereas conventional combustion tends to have, it'll have one all over the place, and you'll be able to identify that this one's reading perfectly, but this one is not, so it must be over here. So there's a little bit of both. And I think that's why in the end you end up with the practical implication of saying, I love the idea of a laser or a couple of lasers up here, but I'm also going to put some strategic conventional combustion down below to help me diagnose and understand what's going on at the bottom, because I don't work under ideal conditions all the time, particularly at turn down, if you're running at half load or something like that.
Yeah, and that's a good point. And there's a question that just came up that really just touches on that comment on the sampling efficiency of the laser beam over a long distance versus close coupled extractive sampling from the gas stream. And it's exactly that. You hit the nail on the head. When we're talking about a laser, you think of it as the average concentration across the length of the laser. We have no indication as to where potentially an upset might be taking place. We could have the same potential absorption from a high concentration in a very small area as maybe a low concentration over the entire width of the laser or distance of the laser beam. They could potentially give us the same signal. The advantage there is that you won't miss anything. There won't be gaps in the coverage. The flip side is you don't necessarily know where it's going to be. You could see using those two technologies to help you pinpoint where the problem is.
Great. Okay. And then kind of a question for both of you guys. What kind of process conditions are you looking out for when you choose either technologies? What are kind of red flags or green flags?
I think with the laser, we're probably a little bit more constrained. I would say, in the sense that it has to work, right? We can't be in a situation where the signal doesn't get across. So, for example, high particulate loading can be a challenge. If we had condensing vapors within the sample, in other words, it's raining in the stack, for example, well, that's something that potentially obscures the light signal from getting from one side to the other. Those are certainly challenges to be looked at. Sounds like we have an Amber Alert. And then back to the equation, the Beer-Lambert equation, we're always looking at that balance between the concentration we're trying to measure and the distance that we have to cover. And does it fit within the constraints of what we can do within a single instrument? There are limitations potentially there. Rarely, I would say, for combustion. Combustion is one of the more robust data or sets of lasers. It works really well with the types of conditions that we see in terms of being able to measure percent level oxygen, ppm level CO, and potentially percent level methane in those applications usually pretty well. Stu, do you want to talk about the constraints when it comes to
there's no real sort of easy, bad conditions are bad conditions for any analyzer, but the industry itself has sort of ironed out the problem. If it's wet and raining and high dust particulate, then you have to manage it. But what's nice with an extractive analyzer or semi-extractive is we're sort of in control of that process. And as long as we get gas out and gas back in at the process conditions, i.e. non-condensing and not sucking too much particulate in, then generally speaking, those analyzers are quite forgiving in terms of continuing to give a reading. And it's more relating to sort of where you want to put it rather than where you rather than the conditions inside. And historically, there's always been a little bit of a problem related to analyzers being too far away from a convection zone. And I know I've talked a lot about that with combustion engineers, and it speaks to the history of the industry. But really, we want to be further down where it's a little bit hotter. We prefer the heat, and we don't like the heat. Rather be down hotter, closer to the action, being able to respond quicker at those conditions further down. So on new conditions, you want to push yourself a little closer to the zone, to be honest. I'm looking at a question in the chat here, which speaks to that.
That question kind of.
How many analyzers do you want? And I think from a practical point of view, the answer is as little as you can get away with, from a cost preventative point of view. But the idea is, with all process analyzers, I think they do their best work delivering the reading that you don't want them to deliver, i.e. when things aren't going well, a process analyzer tends to give you the best answers because it helps you to diagnose the problem and get over it quickly and get beyond it, get safe, get efficient, get clean, whatever that answer is. It's when the process is not working. So if you imagine ideal conditions, then you tend to see less requirement for measurement. If you imagine in ideal conditions, then you tend to see more. And I know that sounds silly, but if you have, say, 10 burners at the bottom, and it's very critical that all 10 of them are lit beautifully and working perfectly, then you might want to make sure that you have enough analyzers to be able to view them all in a reasonable number of sections. Or you want to make sure that when you turn down at half load, that you are still able to see good reading. Or you can imagine over time this boiler is old and I'm sucking in a lot of air. So if I'm measuring up top, I'm probably getting somewhat spurious readings. So I want more readings down below to be able to equate the two. So it's an imperfect science. And it sort of speaks to where lasers have come in, which is to say, if I've only got 2 or 3 down here, can I miss information? Yeah, possibly. But if you put a laser up here, you're going to have that last catch-all, which means at the last minute you can be relatively confident that you didn't miss everything, that even the ones down here didn't do the job. So I think it's more looking at it from that point of view, is to say, if things went badly, where would I want to know the information? And then you sort of work your way back from there, I think. JC?
Great. We've got
Absolutely.
1 minute left.
And 1 minute left. It ties in a little bit with the next question as well about the temperature, 1400 degrees C. The short answer is that's manageable. That's not an issue from either technology's perspective. In the case of the, I'm speaking for you, Stuart, in the case of the traditional analyzers, it really comes down to what kind of probe are you going to use, the metallurgy. You don't want it breaking off or sagging or anything like that. With the lasers, if there's a benefit, it's that everything is outside of your process. There's nothing in the process. So as long as we can protect the instrument from radiant heat and things of that nature, it's fine. There is a spectroscopic limitation to the measurements sometimes, but again, by good fortune, these measurements for combustion applications are regularly done at these types of temperatures. So it speaks a little bit to what was talked about before, about that wanting to get down closer and closer to the combustion zone for better information. And these technologies both adapt themselves well to being able to do that. We no longer are constrained by the fact that it's an in situ measurement where we have to be below 600 C or maybe even lower, and therefore we're doing the measurement way up the stack potentially. We can get down much closer to the actual combustion zone.
My one final comment on this would be an awesome slide that we use all the time, which is temperature loss across metal. And we have a slide from a manufacturer of metal probes that says from 304 degrees C to 34 degrees C in 10 inches. I can hold it at one end and have it burning hot at the other and lose that temperature. Now that I live all the way away from my original home in Alberta, temperature loss is a massive problem for us. The shortest amount of standoff can drop enough temperature to cause us problems. So to be honest, we like heat. Heat is our friend. We can deal with it being a little bit too hot and lose that heat very fast if we want to. But not hot enough is usually our problem. So high temp, we're good with that. I think we're at time, Felix.
Yeah. So we can definitely wrap it up. I think we wouldn't mind staying around if there's other questions, but good answers, good questions as well. Thanks, everyone. Feel free to reach out to any one of us. I think Gada is going to be sending the recording shortly. So thank you all
I would add
for
from my
watching.
side, sorry, I'd add from my side that, it is a massive subject with a lot of conversation, and we're always very happy to talk it through with anybody. So anyone online that wants to reach out individually and have a conversation or do a little bit more training, we're always more than happy to do any of that stuff with anybody. In fact, it's part of the things that JC and I love to do is a little bit of team training and so on. So thank you. Thanks, everyone. We really appreciate the time.
Thanks for joining us.
Thanks, everyone.
Thank you.